You are floating. The water is warm, blue, and completely still. Below you, a reef stretches in every direction. Staghorn coral, brain coral, endless columns of fish moving in tight silver clouds. It is breathtaking. It is also, in this imagined world, wrong. Something is missing. Something that has been here for 400 million years is suddenly gone. You just don't know it yet. This is what the ocean looks like without sharks. Sharks have existed on this planet since before trees. Let that land for a moment. Trees evolved roughly 360 million years ago. Sharks were already ancient by then. They survived the asteroid that killed the dinosaurs. They survived 4 of the 5 mass extinction events in Earth's history. They are, by almost any biological measure, the most persistently successful large predators the planet has ever produced. And right now, today, roughly 100 million of them are killed every single year, mostly for their fins, and mostly by us. So the question is not hypothetical. It is a preview. What actually happens when they disappear? Let's find out. To understand what sharks do, you first have to understand what apex predators actually are, and why removing them breaks things in ways that take years, sometimes decades, to become visible. An apex predator is an animal at the top of its food web with no natural predators of its own. But that definition misses the more important point. Apex predators do not just eat things. They control the behavior of everything below them. When a shark is present in a reef system, the animals it hunts do not just get eaten less. They move differently. They graze differently. They choose different parts of the reef to inhabit. The shark does not have to kill anything to shape an entire ecosystem. Its presence alone is enough. Marine biologist Ransom spent years studying this effect before his death in 2007. His landmark research, published in Science in 2007 alongside Boris, traced what happened to shark populations along the eastern coast of North America as large shark species were commercially overfished across the late 20th century. What they found rewrote how marine scientists think about predator loss. As great sharks, bull sharks, tiger sharks, great whites, hammerheads, declined by more than 90% in some areas, the animals those sharks had historically eaten began to explode in number. Specifically, cownose rays. Cownose rays eat scallops. As shark numbers fell, cownose ray populations grew 32 times larger than normal. Those rays consumed the scallop populations of the entire Chesapeake Bay. A century-old commercial scallop fishery, gone. Not because of overfishing. Because a predator that kept the rays in check was no longer there. This is called a trophic cascade. Trophic means relating to feeding. A cascade means the effect moves downward through the food chain in waves, level by level, each removal triggering a collapse in a level below it. When you remove a shark, you are not removing one animal. You are removing a keystone from an arch. And the arch falls in slow motion. So let's reconstruct what that slow fall actually looks like. Day 1, the sharks are gone. Nothing dramatic happens. The reef looks identical. The fish still move in the same patterns. The coral still catches the light the same way. You would not notice anything different if you dove there tomorrow. Week 3. The mid-level predators, the rays, the groupers, the jacks, the barracuda, begin to sense the absence. Not consciously. Their bodies simply stop receiving the chemical and behavioral cues that normally constrain where they feed and how long they stay in one place. Slowly, almost imperceptibly, they start feeding more. More boldly. More often. Longer sessions at the reef. Month 4. The herbivorous fish, the parrotfish, the surgeonfish, the damselfish, are being eaten faster than they reproduce. These are the animals that graze on algae. They are the reef's lawnmowers. Their populations begin to fall. Month 8. Algae begins to bloom. Without enough herbivorous fish to keep it cropped, algae spreads across the reef surface. It competes directly with coral for space, for light, and for the calcium substrate both need to grow. Coral grows slowly. Some species no more than 1 centimeter per year. Algae grows fast. In the competition for a reef surface, algae wins. Year 2. Significant sections of the reef have shifted from coral-dominated to algae-dominated. Marine scientists call this a phase shift. It is one of the most studied and feared outcomes in reef ecology. William Friedel and subsequent researchers at institutions including NOAA's Coral Reef Ecosystem Program have documented these phase shifts across degraded reefs in the Caribbean, the Indo-Pacific, and the Gulf of Mexico. Once a reef tips into an algae-dominated state, It is extraordinarily difficult to reverse. The ecosystem does not simply bounce back when conditions improve. It holds. Because algae prevents new coral larvae from settling. The reef that took thousands of years to build begins to functionally disappear within a few human lifetimes. And that is just what happens at the reef. Sharks do not only inhabit reefs. They patrol open ocean. They cruise coastal shelves. Great whites range across entire ocean basins. And in those open waters, their role is different but no less critical. Sharks are, among other things, the ocean's disease management system. They preferentially target sick, injured, old, and genetically compromised animals. This is not charity. Sick prey is easier to catch. But the effect of this selective predation is that the gene pools of prey species are continuously purged of their weakest individuals. The animals that survive are the fastest, the healthiest, the most disease-resistant. Remove sharks, and that selective pressure disappears. Marine mammals, large fish species, and sea turtles all begin carrying higher burdens of parasites and infection. Disease transmission rates within those populations rise. The populations become less resilient, not immediately, but inexorably, over generations. There is also the matter of marine snow. When large animals die in the ocean, whales, large fish, sharks themselves, their bodies sink to the seafloor and release enormous quantities of carbon that have been stored in their tissue. This carbon sinks out of the ocean's upper layers, where it would otherwise contribute to acidification and warming, and becomes sequestered in deep sediment. Marine biologists call this the biological pump. Sharks play a role in this pump by keeping prey populations healthy enough to be large, fat, and carbon-rich when they die. A collapsed prey population, sick, small, and nutrient-depleted, delivers far less carbon to the deep ocean when it dies. The ocean's capacity to absorb and sequester atmospheric carbon diminishes. This is not a metaphor. A 2019 study led by researcher Trisha Atwood at Utah State University estimated that the global loss of marine megafauna, large ocean animals including sharks, has already reduced the ocean's carbon sink capacity by measurable amounts. The ocean is not just a habitat. It produces more than 50% of the world's oxygen, more than all the world's forests combined. It absorbs roughly 30% of the carbon dioxide humans produce every year. When the systems that maintain the ocean's biological health begin to fail, those numbers move. In ways no terrestrial ecosystem can compensate for. Here is the counterintuitive part that most people miss. We tend to think of sharks as dangerous to us. The instinctive response to their decline is something close to relief. Fewer shark attacks. Safer beaches. What is there to mourn? But sharks kill roughly 5 to 10 people globally per year. Tragic for those families, statistically negligible at a species level. Humans kill 100 million sharks every single year. The danger in this relationship is almost entirely flowing in one direction, and it is not flowing toward us. The real danger is the reef that is not there. The fishery that collapsed. The oxygen yield that quietly fell. The carbon sink that quietly shrank. These are the consequences that move in slow motion, that appear on no single news cycle, and that are vastly harder to reverse than they were to cause. Sylvia Earle, oceanographer and National Geographic explorer in residence, has spent decades making this argument. She calls the ocean a life support system, not poetically, but literally. Remove enough of the biological machinery that keeps it running, and the system does not give dramatic warning. It just gradually, incrementally, loses function. You are still floating. The water is still warm. The reef below you still catches the light. But you know now what you are actually looking at, an ecosystem in which every animal, every coral polyp, every microscopic alga is participating in a system of unimaginable complexity. A system that spent 400 million years calibrating itself, with sharks at the top, keeping it in balance. The ocean without sharks does not look dangerous. It looks beautiful. That is what makes it so easy to lose. And that is exactly what the shark has always counted on you not understanding.